Hello students, this is Professor Chalai, and in this video we're going to look at non-ideal gas behavior. As always, you can follow along with our Chapter 9 workbook. By the end of this video, you should be able to describe the physical factors that lead to deviations from ideal gas behavior, and also quantify various gas properties using the van der Waals equation. Let's get started. Now, so far we've been using the ideal gas law and the ideal gas equation. Just as a reminder, that ideal gas law equation is PV is equal to nRT, which we probably should have memorized by now. But there's a reason that we call it the ideal gas law gas equation and not the real gas equation. That's because real gases vary from the ideal gases in some important ways. But perhaps the most important deviation is the fact that gas molecules don't just bounce off of each other and not interact at all, but they do interact. In fact, they interact through what we will call van der Waals interaction. And we'll learn more about this in the next chapter, but here just know that gas molecules, all gas molecules, would attract each other just a tiny bit. So if we look at our ideal gas law equation again, PV is equal to nRT, well, how is pressure and volume affected by this interaction between gas molecules? Let's look at volume to start with. So that's what these two images are showing. So if you have a bunch of gases filling some volume, real gases affect the volume in two ways. One, in the ideal gas law, or the kinetic molecular theory of gases that we talked about in our previous video, we talked about how gas molecules have negligible size. But this is not true because we know that gas molecules have some size. They're very small, but they have some size. Secondly, so the fact that these gas molecules have some size means that they will take up some space, so this volume that they have to move about in is smaller. Secondly, the gas molecules are interacting with each other, right? So they're pulling each other in closer than would be in an ideal gas situation. And so really the volume that these gases would need to be in order to have the same pressure would be smaller because they're pulling each other in just a tiny bit. Now let's look at pressure and how pressure is affected in a real gas compared to an ideal gas. So in an ideal gas, we talked about how gases just sort of bounce off of the walls of the container, and that's what pressure is, which is all good. However, now in a real gas, these gas molecules, apart from zipping around, they're also slightly attracted to all the other gas molecules around them with van der Waals interactions, right? So what this means is it's not going to bump into this wall with as much force because all these other molecules here are pulling it backwards, just a tiny smidge, because they have some pull on them. So the force that they exert on the wall of the container will be just a tiny bit smaller, so the pressure is just a tiny bit smaller. So that's summarized here in these two sort of points, that real gases reduce their overall volume, and in real gases the impact is reduced, which means the overall pressure is reduced. So instead of having this PV is equal to nRT equation, we need to account for those sort of reduced pressure and reduced volume. And to do that, we use what we call the van der Waals equation. Basically, it's a modified ideal gas law. It takes the ideal gas law and we modify it just a tiny bit. How do we modify it? Well, let's look at pressure. So pressure we have here in blue, right? Instead of just regular pressure though, we change the pressure. We add this little term to account for how much the pressure is reduced. N is the number of moles, as always, is the same N as over here. V is the same V as over here, that V hasn't changed. But this A factor is a factor that accounts for the van der Waals interactions between particles, right? So it tells you how much the particles are being held back from hitting the walls. And so this would depend on the specific kind of gas that you have. Right? If you have a gas that interacts very strongly, then that A value would be very large. If the gas interacts very weakly, that A value would be very weak. But for gases, well, let me just show you. We have an entire table of these. So here we see that all of these gases, like nitrogen and oxygen, interact pretty much on the same level. Carbon dioxide has a little bit stronger interaction. Here, water has the strongest interaction of all. Whereas helium, we know helium barely interacts with anything. It has a very weak interaction with each other. So that's the A value. Here are the units. That tells us how much the pressure is reduced. For the volume, we mentioned how the volume is also reduced. Here's how we reduce it in the van der Waals equation. We take V and we subtract it with this term here, that's the number of moles, N, times this constant B. Constant B, again, is just related to, like, somewhat related to the size of the particle. So if you have a tiny particle, that B value is tiny. You have a larger particle, that B value is slightly larger, and for an even larger particle, it's even larger than that. But B is somewhat related to the size of the particle, but again, we're not going into details of what A and B are beyond just the attractions between particles and the size of particles. So I'll just write that here. A is not red, I want A in blue because that's what it's in. A is somewhat related to the van der Waals attraction, mostly. There's other stuff in there. And B is somewhat related to the size of the particle, mostly. So that's how we change the pressure. Instead of regular pressure, we have this term for pressure. Instead of regular volume, we have this volume. And then the nRT term is just the same. So that's how we modify the PV is equal to nRT when we want to talk about real gases. And in those cases, we need to know what A is, we need to know what B is for that gas. And this table here just lists some common gases and the values for A and B for those gases. So let's do some practice here by trying to answer numbers 45 and 46. Try them on your own. You have the equations, you have the constants in the table. I think you can handle this one on your own. So try to pause the video, work through them together, and then we'll go over them. We'll go over them together. Okay. Let's look at number 45. Number 45 says we have a 4.25 liter flask, so that's already the volume, 4.25 liters. Let's make this a little bit bigger so I can write a little bit neater. They give us the number of moles, so that's cool. So that's the volume, that's the number of moles. So number of moles is 3.46 moles. They give us the temperature, but it's not in Kelvin, but we can do that. We can make it into kelvins easily. We add 273, and this gives me 502 kelvins. And what else? We got V, we got N, we always know R, and they want us to calculate the pressure. Okay, so this is the ideal gas law, so we know that the pressure is equal to nRT. PV is equal to nRT, which means that the pressure is equal to nRT over V. So let's write that. The pressure is equal to nRT over V. So let's just plug in numbers, right? That's all that's left. N is 3.46 moles. R we know is 0.08206 liters times atmospheres over moles times Kelvin. T is the temperature, which we happen to calculate as 502 kelvins. And then V is the volume, which is 4.25 liters. So time to cancel out units. Let's see, moles, moles, Kelvin, Kelvin, liters, liters. We're left with atmospheres as the pressure, which is completely fine by me in this equation. So I end up with, to 3 sig figs, 33.5 atmospheres. Okay, so that's using the ideal gas law. What about the van der Waals equation? Let's look at that. So the volume, number of moles, temperature are all the same. But what are different? We're looking at CO2. So the A value for CO2 is 3.59 liters squared. So the units are up here, liters squared times atmospheres divided by moles squared. And then B is 0.0427 units of liters over moles. So let's use the van der Waals equation now with these constants included. So let's see. We know that the van der Waals equation has P plus AN squared over V squared, right? All of that times V minus NB is equal to nRT. We want to solve for the pressure, so now it's a bunch of algebra. If we divide both sides by this term, V minus NB, we get that. And then we need to subtract this guy on both sides. AN squared over V squared. And so this is what P is equal to. Let me rewrite that in a different color. P is equal to nRT over V minus NB minus AN squared over V squared. Now it's just substitutions, right? So let's come back up over here. P is equal to, I forgot what N was. Let's see, N is up here, 3.46 moles, so 3.46 moles times R, 0.08206 liters times atmospheres over moles times Kelvin. nRT, the temperature was 502 kelvins. Instead of dividing by V though, we're dividing by V minus NB, so V was 4.25 liters. Minus NB, so N is number of moles, which we said was 3.46 moles. And B, we had was up here as 0.0427 liters times over moles. All right, I know this equation seems long, but it just requires some working through. Now the negative part, AN squared over V squared. So A is 3.59 liters squared times atmospheres, there we go, over mole squared, times N squared. N squared is number of moles, so it will be 3.46 moles squared, 3.46 squared times mole squared, right? Over V squared, which is 4.25 squared times liter squared. All right, well, it seems like a lot of stuff, but things just start to cancel out nicely now. Moles with moles, Kelvin with Kelvin, liters with liters there, and then moles with moles here, liters with liters there. So we're left with atmosphere in this left-hand part. Let's see what about the right-hand part. Liter squared with liter squared, mole squared with mole squared. So we're left with just atmosphere again, which is great. So remember, this is 3.59 times 3.46 squared divided by 4.25 squared, right? Never forget the squares. So this all comes out to, if I plug all of those numbers in my calculator, I get something like 32.4 to 3 sig figs, right? Atmospheres. So remember we talked about how in real gases the pressure is just a tiny bit weaker than in ideal gases. Here's the example of that. For this case of carbon dioxide gas, if we use ideal gas law, we got a pressure of 33.5 atmospheres. If we use the van der Waals equation, which is for real gases, we get just a slightly reduced pressure of 32.4 atmospheres. All right, do number 46 and see what you get using the same equations that we've used in our, in our previous question. All right. Let's see, number 46, our volume is 560 milliliter, but we want this in liters, so this is 0.56 liters, right? 2 sig figs. They give us the mass, so we know that we can convert mass to number of moles. So let's do that right away. It's for nitrogen gas, so the molar mass for nitrogen is 28.02 grams per mole. So this should give us number of moles as, let's see, 0.760 moles. They give us the temperature, but not in Kelvin, so we can do that though. 145 plus 273 gives us 418 Kelvin. That's it. So let's calculate the pressure. So we know that PV is equal to nRT, or rather P is equal to nRT over V. So let's substitute things. We got N is 0.760 moles, R is 0.08206 liters times atmospheres divided by moles times Kelvin. T was 400 and I don't remember, 418, there we go, 418 kelvins. And volume was 0.56 liters. 0.56 liters. So cancellation moles, moles, Kelvin, Kelvin, liters, liters, and pressure is in atmospheres, which is what we expect. 3 sig figs, 2 sig figs, we get 2 sig figs. So it's about 47 atmospheres to 2 sig figs. Okay. Let's look at from the van der Waals equation. So we're looking at N2, so we need the value for A and we need the value for B. So the value for A, according to the table, right, table all the way up here for nitrogen, the value for A is 1.39 liters squared times atmospheres divided by moles squared. The value for B was 0.0391 liters over moles. So if we wanted to find the pressure using the Van der Waals equation, I'm not going to do all these steps again because we just wrote the equation here for the Van der Waals equation to solve for the pressure. It's nRT over V minus NB minus AN squared over V squared. I did not memorize that. I just used it so much that I guess I did memorize it. All right. Now it's just substituting, right? N is, what is N? Forgot what is N. There we go, 0.760, so 0.760 moles. R is 0.08206 liters times atmospheres over moles times Kelvin. And again, if you've done all this and you got the correct answer, you can just skip ahead to, well, skip ahead to verify the answer, but the temperature is 418 Kelvin. I just want to show every single step so that the people, some students are not missing steps. The volume is 0.56 liters. We're minusing this N times B factor, so that's 0.760 moles times the B factor, which is 0.0391 liters over moles. All right, so that's all the first term, and then let's minus the second term with A, which is 1.39 liters squared times atmospheres divided by mole squared times mole squared, right? Moles was 0.76, so that's 0.760 squared times mole squared. And the volume is 0.56 liters, so it's 0.56 squared times liters squared. Whew, that's a lot. Now, we've done this before. The units should all come out to atmospheres, but let's make sure. Moles, moles, Kelvin, Kelvin, moles, moles, liters, and liters, and liters. Right? These are two subtracted, so that's why I did that. Mole squared with mole squared, atmospheres with, nope, atmospheres does not go anywhere. Liter squared with liter squared. All right, so we punch all of these into our calculator. Remember, we need 2 sig figs over here. 2 sig figs. So we punch all of this into our calculator and also get 47 atmospheres. After all that hard work, it looks like the pressure with the ideal gas law is 47 atmospheres to 2 sig figs. The pressure with the Van der Waals equation is also 47 to 2 sig figs. This is one of those situations where the real gas, because of the amount of gas that we have or the volume, behaves exactly like an ideal gas. So when does that happen? Well, let's go back to our equation. If A is small, right, or B is small or 0, then this equation is the same as the ideal gas equation. But let's ignore A and B. Let's say we're comparing the same gas. When does it behave like an ideal gas, and when would it start to behave like a real gas? Or rather, when does it start to behave like an ideal gas? Well, look at this term right here. It's in the denominator. So if the volume gets larger and larger, this whole thing goes to 0. So it's like it doesn't exist. So if you have a very large volume of gas, then it starts to behave more and more like an ideal gas, right? On the other hand, if you have a very, very small number of moles, right? Let's say this number of moles is going smaller and smaller, closer and closer to 0, then this term would go away and this term would go away. And again, it looks like we have an ideal gas. So those are the two situations where a real gas can behave like an ideal gas. We have a large volume or a small number of moles, or a combination of both. All right, so this will bring us to the end of gases. We've learned a lot of things about gases, about pressure and the kinetic molecular theory of gases, the different gas laws and how they're used, how gases are used in stoichiometry and reactions. And then finally, we looked at real gases and how they change from all the things we've been studying before in this chapter. All right, there's a lot of questions at the end of all of my chapters, as you know, for practice. So, if you want more practice with these sorts of questions, please take a look at that. Otherwise, if you have other questions, let me know, and I will see you in the next chapter.